Hello dear students, welcome back to the discussion of NCERT line by line questions. Today we discuss chapter number 7th, alternating current. The first question is, a 10 by pi microfarad capacitor is connected to a 200 volt, 50 Hz AC source. Capacitor of capacitance C is equal to 10 by pi microfarad. Okay, this is connected to an AC source whose RMS voltage is 200 volt. RMS voltage is equal to 200 volt and the frequency is 50 Hz. Okay. The capacitive reactance of the circuit is capacitive reactance. What is the capacitive reactance? XC. XC is equal to 1 by C omega. That is the equation. Very direct. 1 divided by C omega. That is equal to 1 by C into omega is 2 pi nu. 2 pi into frequency. Omega is equal to. Clear? Capacitance is given, frequency is also given. Okay. This is equal to 1 divided by capacitance is 10 by pi micro. Micro means 10 power minus 6 into 2 pi into frequency of the AC source is 50 Hz. 50. Okay. Yeah. Pi is cancelled. Clear? 2 into 50 is 100. 100 into 10,000, that is 10 raised to 3. 10 raised to 3 into 10 power minus 6, that is 10 power minus 3. Okay, to the numerator, that will be 10 raised to 3. So this is equal to 10 raised to 3, that is 1000. Okay, 1000 ohm. Okay, what is the SI unit of capacitive reactance, inductive reactance, etc. is ohm. Okay, those symbols are the resistance offered by the corresponding component to the circuit. So answer is option A, 1000 ohm. Clear? Very direct question. The next one, a light bulb is rated as 100 watt for a 220 volt 50 Hz supply. A bulb is rated as 100 watt at 220 volt 50 Hz. What is the meaning? The power of the bulb is equal to 100 watt when we apply. When this power will be, okay, this is not the power always. This much power the bulb consumes when we apply an RMS voltage of 220 volt. At this voltage, the power consumption is 100 watt. That is the meaning of power rating. Okay, from these data, we get the idea of the resistance of the bulb. Okay, this is VRMS value and this is the power at this voltage. Then we get the resistance of the bulb. Okay. The question is, the RMS current through the bulb is dash. The RMS current through the bulb. Okay. In terms of RMS current and RMS voltage, what is the expression for power? Power consumed is equal to VRMS into IRMS. Okay. VRMS into IRMS. This is the power consumption. Okay. Yeah. Now, IRMS is asked. Very direct question. Power divided by VRMS. Okay. Yeah, power is equal to 100 watt divided by VRMS is 220 volt. Okay, yes. 0, 0 cancel. 10 by 22 is 5 divided by 11. 5 divided by 11 ampere. This is option 2. Very direct. 5 divided by 11 ampere. Clear? So easy. The next one, an AC signal output from a device is shown in the figure. Okay, the average value and the RMS value respectively in the given case are. Clear? This is a sinusoidal wave, a half wave sinusoidal wave is given in the figure. Okay, the peak value of the current is I0. Clear? The peak value of the current is I0. Okay, Then what will be the RMS value? RMS value IRMS is equal to the peak value divided by root 2. We studied it, that relation. So the RMS value is directly obtained, that is I naught divided by root 2. Clear? I naught divided by root 2. There are two options, I naught divided by root 2. First one and second one. Clear? Yes. Now, in the case of this half wave rectification, the average value is equal to. What is the averaged? Average value, how we get the average of a function? Okay, suppose we are having a function f of t. Okay, this is a function of time. Clear? Then what will be the average of this function during a time interval from 0 to t second, for example? Then average value of this function is mathematically written as f average is equal to integral of f of t dt. F of t dt. From 0 to t time interval, we have to integrate this function from 0 to time interval divided by the total time interval. Okay, this is the way, the mathematical way of finding the average value. Clear? In this way, a half wave sinusoidal wave, when we take the average during this half wave, see, this is the time 0 and this is the time t by 2. See, this is the time 0 and this is the time t by 2. Okay, and let this function be I is equal to I0 sin omega t. Okay, I is equal to I0 sin omega t. Okay, then when we perform this mathematical operation, we get this answer I naught by pi only. Okay, this is mathematically very simple to do. You can easily check that. This is the answer, the averaged data. See, this function of time here we can place as I naught sin omega t. I naught sin omega t. Okay, and this time interval here from 0 to t by 2, 0 to t by 2, all divided by t by 2. We get the answer I naught divided by pi. Okay, yes. The next one, question number 4. The instantaneous values of alternating current and voltage in an AC circuit are given as I is equal to, the instantaneous value I is equal to 1 by root 2 into sine of 100 pi t. 100 pi t. This is the instantaneous current given, and the instantaneous voltage given as E is equal to root 2 into sine of 100 pi t plus pi by 3. Good. Question is, the average power dissipated through the circuit is, the average power dissipation. The power dissipated is equal to what? IRMS VRMS into cos phi. This is the power dissipation. Okay, IRMS VRMS into cos phi is the power dissipation through the circuit. Clear? What about this phi is the phase difference between the voltage and the current. Here, current is given in sine argument and voltage also in sine argument, and the phase difference of these two is pi by 3. Okay, that is the phi value. Pi by 3 radian means 60 degree angle. That is the phi value here. Cos 60 degree is 1 by 2. So this is 1 by 2. Clear? The IRMS is Im by root 2 and VRMS is also Vm by root 2. Okay, so this average power through the circuit is Im by root 2 into Vm by root 2. That is Im into Vm divided by root 2 into root 2. That is 2. Isn't it? Yeah. Now cos pi by 3. Cos pi by 3 is how much? That is 1 by 2. Or cos 60 degree 1 by 2. Clear? Yeah. The Im is equal to, what is Im is equal to? The peak value of current is 1 by root 2 and Vm is root 2. Im is 1 by root 2 and Vm is root 2. Then cos pi by 3 is 1 by 2 divided by, here is a 2 here. Okay. Yes. Root 2 cancelled. Okay. 1 by 2 into 1 by 2. It is 1 by 4. 1 by 4. Okay, and the SI unit of power is watt, isn't it? Power is watt. 1/4 watt is the answer, option 2. Clear? Yes. Next one, for a series LCR circuit, the power dissipated at resonance is, see, the maximum power is dissipated at resonance. Okay, see, the power dissipated at resonance is, at resonance, what will be the impedance of the circuit? The impedance of the circuit will be minimum and it will be the resistance. R is equal to, we have the impedance of an LCR circuit is root of XC minus XL the square plus R square. Clear? Yes. The first term XC minus XL is called reactance of the LCR circuit. Okay. Now at resonance, what the condition is that XC is equal to XL. See, XC is equal to XL. Clear? At resonance, we have XC and XL are equal and this term will be 0 and root of R square is R. That will be minimum impedance happening and that is a condition known as resonance. Okay. Okay. Now the power consumed is, what about the power consumption? Power consumption is equal to via IRMS square into Z. We can say that in terms of current, IRMS square into impedance. This is the general expression for power consumption. Otherwise, VRMS square by Z. VRMS square by Z. If not, IRMS into VRMS into cos phi, as we did in the previous question. Clear? So these are the formulas, IRMS square into Z or VRMS square by Z or IRMS VRMS into cos phi. Yes. Now here Z value is equal to R. Then what it will be? The minimum power is IRMS square into the resistance. That is the power consumption at resonance, IRMS square into R. Okay. Yes. Moving to the next one. The primary winding of a transformer has 200 turns. In the primary winding of a transformer, the number of turns in the primary of a transformer, NP, is equal to 200. Okay. Whereas its secondary winding has 2000 turns. The number of turns in the secondary is equal to 2000. Good. If the primary is connected to an AC source of 20 volt and 60 hertz, what is the applied voltage? The voltage applied across the primary, that is represented as VP. Let it be VP. The voltage applied across the primary is 20 volt. Okay, and the frequency of the AC is 60 hertz. Okay, then the secondary will have output of, what will be the secondary voltage? We have the expression of Vs by Vp. Vs by Vp is equal to Ns by Np. Turn ratio of a transformer, Ns by Np, that is equal to Vs by Vp. The voltage across the secondary is equal to, voltage across the secondary is equal to Ns by Np into Vp. Very direct. Ns is 2000, Np is 200, then Vp is 20. Okay, 2000 by 200 is 10, 10 into 20 is equal to 200 voltage. Means the voltage is increased by 10 times. Since the number of turns is increased by 10 times, then the voltage will be increased by 10 times 200 volt and there won't be any change in frequency. Frequency remains same. Okay, no change in frequency. So the answer is 200 volt, 60 hertz. That is the output. Okay, yeah. The next one. An AC supply is connected across a series LCR circuit. Clear? If capacitor is removed, there was series LCR circuit initially and then the capacitor is removed. Then what it remains there is LR circuit, inductor and resistor. Okay, the remaining is LR circuit. LR circuit, inductor and resistor. Okay. Now, then which of the following phasor diagram may be correct? See, in the case of LR circuit, we studied that current lags behind voltage. by 90 degree angle, by a phase difference of 90 degree. Which one is leading? Voltage is leading and the current is lagging. See, in all of these circuit, alternating circuit, for example, resistor only, capacitor only, inductor only, or LR, CR or LCR, in all of these, we are applying the AC voltage as V is equal to Vm sin omega t. Suppose we can take so. V is equal to Vm sin omega t. And we are checking the expression for the current. How the current in the circuit, whether it is leading or lagging, or whether it is in the same phase, that only we are checking. And in the case of resistor only circuit, we studied that current is in same phase with the voltage. Okay, and in the case of inductor only circuit, see, in the case of inductor only circuit, what happens? In the case of inductor only circuit, the current is lagging behind the voltage. Okay, now here capacitor is removed and we have an LR circuit. An LR circuit means there will be voltage across resistors. See, I can draw this. An LR circuit, a resistor of resistance R and an inductor of inductance L connected in series to an AC source. This is an LR circuit. Clear? There will be voltage across resistor and voltage across inductor. Clear? Now, there will be current through the circuit. Definitely. The current through the circuit is the alternating current I. That is the instantaneous current now represented by I. Okay. Now, the voltage across resistor and the current are in same phase. They are in same phase. Voltage across the resistor and current are in same phase. But the voltage across the inductor is leading the current. Okay, that is the theory we studied. Then what will be the phasor diagram? See, we draw the phasor diagram. Suppose we draw the phasor diagram. Clear? This is the phasor diagram. And here, see, suppose we are representing the voltage, or suppose we are representing the current. First of all, the current is represented. Suppose this is the current representation I. Current representation I, then in the same manner will be the voltage across resistor, isn't it? In the same manner will be the voltage across resistor VR because they are in the same phase. Now, the current is lagging behind the voltage across the resistor. The current is lagging behind the voltage across the inductor. Yes, the voltage across the inductor, then it will be in this way. Voltage across the inductor VL, and the voltage is leading and the current is lagging by 90 degree angle. Now check. What will be the resultant voltage? The resultant voltage will be the vector sum of this VL and VR. Vector sum of VL and VR, that will be somewhat in this way. See, vector sum of like this. This is the resultant voltage. Now you see, the resultant voltage V is leading and the current is lagging. This is the situation. Okay. The final situation is the voltage in this LR circuit. The voltage in this LR circuit is leading and the current through the circuit is lagging. This is the situation. Now we check the graphs. Here see, the current is here. In the first option there is current and voltage and there is a phase difference of pi by 2. But this is incorrect. Here this is the phase difference between the current and net voltage. It is not pi by 2. Clear? So this option is incorrect. This option is incorrect. First one. Now the second one we check. Here is the current in this direction and voltage in this direction, and there is 60 degree angle, and voltage is leading, current is lagging. Clear? Now this is the possible graph. This graph is possible. Now what about this one? In this case, see, the current is leading and the voltage is lagging. It is incorrect. It is incorrect. And in this situation, see, the voltage is leading and the current is lagging, but the angle is greater than 90 degree. Angle is greater than 90 degree. It is not possible. So the answer is option B. I think you understood it. This is an LR circuit and the phasor diagram of an LR circuit is needed. Okay, its shape is like this. That's the answer of this question. Okay, the next one. The analog of displacement X in mechanical system is P in electrical system. Mechanical oscillation and electrical oscillation. There is a comparison in the textbook. Mechanical oscillation means a spring and a mass connected. Okay, that's mechanical oscillation. And an electrical oscillation is the LC oscillation. Clear? And there is a comparison there in the textbook between the mechanical oscillation and the electrical oscillation. Okay, we can compare those two, the mechanical and the electrical oscillation. Yes, in the case of mechanical oscillation, the quantity which oscillates is X, the position of the block. See, a spring, a block, and the block is made to oscillate. Then X is oscillating. Okay, the corresponding quantity here is, in the case of LC oscillation, the charge in the capacitor is oscillating. Okay, now here dx by dt, that's the velocity. Here dq by dt, that's the current. Clear? In that way the comparison proceeds. Clear? Here the inertia, the measure of inertia is mass. Here the measure of inertia is inductance. Okay, it is the measure of electrical inertia. In that way the comparison proceeds. And now our question, what is the analogous quantity of X in electrical system? In electrical system the quantity is charge. So the answer is option B. Clear? Okay, the next one. A capacitor, say, initially charged up to Qm. The maximum charge put on the capacitor is Qm. Okay. And this capacitor is connected to an inductor. Okay. So what about this? This is LC oscillation. See, the differential equation of LC oscillator is, studied it. The differential equation of LC oscillator is second order derivative of the charge, that is d square q by dt square plus a constant. The constant is here 1 by LC, then q is equal to 0 is the second order differential equation of the LC oscillation. Yes. Clear? In the case of mechanical oscillation, as we discussed in the earlier question, that in the case of spring block system, what was the second order differential equation there? It was d square x by dt square plus k by m into x is equal to 0. This was the equation in the case of mechanical oscillation, studied in work energy power chapter. Otherwise, oscillation, the chapter oscillation in the 11th standard. Okay. Now this term is omega square there, and here this is the term omega square 1 by LC. Okay. Now we have the option here d square q by dt square plus q divided by LC is equal to 0. Answer option D. Very direct question. Okay. Good. The next one. For pure resistive AC circuit, the phase angle between voltage and current and power factor are respectively. Pure resistive AC circuit, that is R only circuit. In the case of R only circuit, the current and voltage are in same phase. We are applying voltage Vm sin omega t. Suppose we are applying this alternating voltage, then we get the current as Im sin omega t. Okay, both are in the same phase always at any time, means there is no phase difference. There is no phase difference means the phase difference phi value is equal to 0. Therefore, the power factor of the circuit cos phi is equal to cos 0, and that is equal to 1. The power factor of the circuit is cos phi, means resistor only circuit consuming maximum power. Understand? So what the phase difference is 0 degree and the power factor is 1. Answer option A, 1. Correct. The next one. A resistor of 100 ohm is connected in series with a resistor R is equal to 100 ohm is connected in series with combination of inductor and capacitor. Okay, so what this will be? This is an LCR circuit. Good. If XL and XC are the reactance of inductor and capacitor respectively, XL and XC. Okay, this is so. These are the inductive reactance and capacitive reactance respectively. Okay. Then the reactance of the circuit will be. What is the reactance of the circuit? See, in the first question, I think we have discussed this. Reactance of the LCR circuit is XC minus XL, otherwise XL minus XC. Okay, which quantity is greater? Put it first. XC or XL, which is greater than, put it first. XC minus XL or XL minus XC, that is the reactance of the LCR circuit. So here is the answer, option B. Okay, very direct. Yes. The next one, 12th. The quantity which measures the sharpness of resonance is. The sharpness of the resonance is measured by quality factor. There is a term. Quality factors. Directly we studied the quality of the circuit or the quality factor. Okay. Yes. If quality factor is greater, then more sharp will be the resonance curve. Means the bandwidth is lesser. Bandwidth is lesser. Okay. That's it. Quality factor. 13th. A steady current of 2 ampere flowing through a resistor produces a heat of 100 watt. Steady current. Steady current means not alternating. Okay. It's a direct current. Isn't it? 2 ampere flowing through a resistor produces a heat of 100 watt. To produce a heat of 400 watt by supplying an AC current through the same circuit, the value of peak current will be. See, in the first case, the current is direct current, steady current. Clear? That is, I is equal to 2 ampere and producing a power of 100 watt in the resistor. From these two data, we get an idea of the resistance. How much is the resistance of the resistor will be obtained, because power is equal to I square into R. Power is I square into R, so we get resistance. Good. Now, in the second case, we are applying an AC circuit, okay, and we have to produce a power of 400 watt. Then what should be the peak value of current is asked. In the second case, this is P1. Okay. The second case, P2 should be 400 watt. Okay. This is produced by applying what? AC current. Okay. Then what is the case of AC? Power. This P2, we can write IRMS square into resistance. IRMS square into resistance. Okay. And here they are asking about the peak current. What is IRMS is equal to? IRMS is equal to IM by root 2. IM by root 2. IRMS is the peak current IM divided by root 2. Clear? So its square is IM square by 2. IM square by 2. Clear? Yes. This is given as 400. 400. Okay. Now we obtain the value of R by 2 from this. You know what is P1 is equal to I square into R. P1 is equal to I square into R. I square into R is obtained as 100 and I is equal to 2, which means 4R is equal to 100. That is the resistance of the resistor is 100 by 4. It is 25 ohm. 25 ohm. Obtained it. Put here IM square by 2 into 25. This is equal to how much? 400. Clear? Now, IM square is 2 into 400 divided by 25. That is 800 divided by 25. Okay, I can write here IM square is equal to 2 into 400, that is 800 divided by 25. Isn't it? Yes. 8 into 100 by 25. What is 100 by 25? It is 4. 8 into 4, 32. 32. This is im square only. Clear? 32 is im square. Then what will be im? Root of 32. Root of 32 will be a value between 5 and 6. A value between 5 and 6. Root of 32. So here is answer option 2. 5.6 ampere. Okay. A value between 5 and 6. Therefore 5.6. It is not the case. You understood already. You understood it already. Because this value is between 25 and 36. That's why the answer will be between 5 and 6. Okay. Moving to the 14th. The variation of impedance of an AC circuit having one of the element. An AC circuit is having one of the element. One of the element means in first graph it is resistor only circuit, in the second graph it is capacitor only circuit, in the third graph it is inductor only circuit, fourth graph also inductor only circuit. So this is only having one of the elements. Yes. With the frequency, the graph is with impedance and frequency. Impedance on one axis and frequency on another axis. What is the correct graph? I think given different, choose the incorrect plot is the question. Incorrect plot is to be selected. Okay. In the case of first graph, resistor becomes a constant. It is not varying according to frequency. That is definitely true. Resistor, resistance, it is not depending upon the value of frequency. This graph is correct. Yes. What about second one? Second one, there the plot of XC versus frequency. We have X is equal to 1 by C omega or 1 by 2 pi F into C. Okay. 1 by C omega. We understand X is inversely proportional to frequency. X is inversely proportional to frequency means a hyperbolic relation. So this graph is also correct. And third one, the plot between XL and frequency. What about XL is equal to L omega, or it is 2 pi F into L. You know, omega is 2 pi F, which means this XL is directly proportional to frequency. XL is directly proportional to frequency, but the graph is in a different way. This is not directly proportional. This situation is. So this graph is incorrect plot, and that is our answer of the question. Third one is the answer of the question. And the fourth one, you see XL and frequency are directly proportional. Very clear from this equation. Okay. So this graph is also true. So the answer of the question is option 3. Good. The next one, 15th. Consider a series LCR circuit in which reactance and resistance are 100 each. When the circuit is connected to an AC source 220 volt 50 Hz. See, this is an LCR circuit. Okay. Reactance and resistance are 100 each. What is the reactance? XC minus XL. Okay, it is 100, and the resistance value R is also 100 ohm given. Good. And the AC source is of 220 volt 50 Hz, means the RMS voltage is equal to 220 volt. Frequency of the circuit is, or AC is 50 Hz. Frequency of the AC is 50 Hz. Okay. Then current drawn from the sources. How much current is flowing through the circuit? Current drawn means the IRMS value to be calculated. IRMS value to be calculated. What is IRMS? Is equal to VRMS divided by Z. Z is the impedance. Okay. IRMS is equal to VRMS divided by Z. Good. And what is Z is equal to? Z is equal to root of. Z is equal to root of XC minus XL all square plus R square. That is impedance. Okay. XC minus XL is 100. So this is 100 square plus 100 square. 100 square plus 100 square is 2 into 100 square. Its root is 100 into root 2. Isn't it? 100 into root 2. And VRMS value is 220 divided by 100 into root 2. Good. 0, 0 cut. 0, 0 cut. 22 by 10 is 2.2. 2.2 divided by root 2. 2.2 divided by root 2. 2.2 divided by root 2. Okay. 2.2 divided by root 2. No option. No option. Then we multiply by root 2 by root 2. Root 2 by root 2. That's good. Root 2 is 2. 2.2 by 2 is 1.1. 1.1 into root 2 is the answer. Here option B. 1.1 into root 2. Clear? That's the answer. Very good. 16th one is, in the circuit shown in the figure, the voltmeter and ammeter reading will be respectively. Source, voltmeter, ammeter are ideal. Okay. See, in the figure, the capacitor has reactance equal to 25 ohm. That is, XC is given as 25 ohm. And the inductor has reactance as XL, that is also 25 ohm. What do we understand from this? Since XC and XL are equal, this circuit is in resonance, isn't it? The circuit is in resonance. Yes. Okay. Then the impedance Z value is equal to the minimum value, that is equal to the resistance value. And resistance value is 50 ohm. 50 ohm given in the question. Okay. Now, they are asking about the voltmeter and ammeter reading. Voltmeter is connected between inductor and capacitor. Clear? So, we have to calculate vector VL plus vector VC. Vector VL plus vector VC. See, in the phasor diagram treatment, we are taking the voltage and current as vectors. Then it is very easy to solve the LCR circuit. We studied it clearly. Okay. Then this vector VL plus vector VC. Clear? These two are out of phase and equal in magnitude. That is the situation in the case of resonance. We studied the phasor diagram as the voltage across capacitor. The voltage across capacitor is in this way. Then the voltage across the inductor will be in this way. And these two are in the opposite direction and in the same magnitude, will be cancelled. When we add these two vectors, will be cancelled. Understand? Then what will be the effective voltage between these 2 points? The effective voltage between those points will be 0. 0, 0. So either of these two is the answer. So voltmeter reading is 0. Okay. Now another one is the ammeter reading. Okay. What is the ammeter reading will be the IRMS value. Ammeter reading will be the IRMS value. Okay. What is IRMS value? See, IRMS value is equal to VRMS divided by Z. IRMS value is equal to VRMS divided by Z. Clear? What about VRMS given 220 volt? Okay. Divided by Z. Z value is R is equal to 50. 22 by 5 is 4.4 ampere. See, 4.4 ampere is the ammeter reading. So the answer is option 2. It's very clear. Okay. Yeah. The next one. In an oscillating LC circuit, Qm is the maximum charge on the capacitor. If at any time the energy stored in the capacitor and inductor are equal, then the charge stored on the capacitor at that instant is. Yes, this is the case of LC oscillation, and a particular situation is arised in which the energy stored in the inductor and in the capacitor are equal. At a particular situation. At this moment, what will be the charge on the capacitor plates is the question. See, we can compare this with the mechanical oscillation. See, in the case of mechanical oscillation, we are having a spring connected to a rigid support and to a block of mass M. The spring having a constant K. Okay. Now the kinetic energy of the block K is equal to half mv square. Okay. It can be written as half K into xm square minus x square, where xm is the amplitude. Okay, this is the kinetic energy of the block. And the potential energy of the block, we can write U is equal to half K x square. Potential energy U is equal to half K x square. Okay, this is just mechanical oscillation. Here the question is asked about electrical oscillation, but first I am comparing this situation with this situation, then it will be very easy. Okay. Now in a particular case where U and K, kinetic energy and potential energy, are equal at what value of x? We can easily check. At a particular value of x, this potential energy and this kinetic energy are equal, then what will be the value of x in that particular situation? Half K is cancelled, which means x square is equal to x sum square minus x square, which means 2x square is x sum square is x sum square by 2, or x is equal to plus or minus x sum by root 2. Is that clear? Okay, 2x square is x sum square, then x square is x sum square by 2, then x is equal to plus or minus x sum by root 2. This is the situation at which the energy of the block and that of the spring are same. Okay, now you come to the case of LC oscillation, where the analogous quantity, the quantity analogous to x, there is Q. Then what will be the value of Q at which the energy of inductor and capacitor are equal? Will be that Q is equal to plus or minus Qm by 2. On one plate it will be plus and on another plate it will be minus. Okay, plus or minus Qm by 2. When this is the charge on the capacitor, Qm by 2, okay, then the energy stored by the capacitor and stored by the inductor will be same. So the answer is Qm by 2 is the answer. This is just a comparison and easily do. Otherwise we can form the formula like this for the energy of capacitor and the energy of inductor like this, and we can equate. Then also we get the same answer. Okay, so this comparison is very useful. Clear? Moving to the next one, 18th. For an ideal transformer, which of the following option is correct? Symbols have their usual meaning. In the case of an ideal transformer, the input power and the output power both are equal. Clear? The input power is Vp into Ip. The output power is Vs into Is. Clear? The input power and output power are equal means the ideal transformer. Vp Ip is equal to Vs Is is option 3. Okay. Accordingly, we have, as per this equation, Vs by Vp is equal to Is by Ip. Vs by Vp is equal to what? Ip by Is, inversely related. Ip by Is. And we studied that Vs by Vp is equal to Ns by Np, directly proportional to the turns. Vs by Vp equal to Ns by Np. Now you look into the other options. Is by Ip is Ns by Np. Is that true? No. Is by Ip is equal to Np by Ns only. So this is incorrect. Now what about this one? Is by Ip is Vs by Vp. Is that true? Is by Ip is equal to Vp by Vs only. So this is incorrect. And what about fourth? Vs by Vp is Np by Ns. Vs by Vp is equal to Ns by Np only. Not in the reverse manner. So this is also incorrect. So our answer is option 3. Okay? Good. The 19th. A radio can tune over the frequency range of 800 to 1200 kilohertz. The tuning range of the radio is 800 to 1200 kilohertz. Okay. If LC circuit has an effective inductance of 200 microhenry, the inductance of the LC circuit in the radio, okay, the tuning circuit of the radio containing an inductor connected in series with a capacitor. There the inductance value is given as 200 microhenry. Okay, 200 microhenry. What should be the range of its variable capacitor? What is the range of the variable capacitance is asked. Okay, frequency is given, inductance is given, capacitance is asked. Okay, what is the formula of frequency? We have omega is equal to 1 by root of LC is the situation of resonance. And when we select a particular channel in the radio, the circuit is at resonance with that particular frequency. That is the condition. Okay, when we select a channel of 1000 kilohertz frequency, at 1000 kilohertz frequency, the circuit is at resonance. We are selecting such a capacitor there by tuning. That's the condition of tuning. Okay, so this is the equation of resonant angular frequency, and we have omega is 2 pi nu. So nu is equal to 1 by 2 pi into root of LC. 1 by 2 pi into root of LC. Then we have nu square. We need the value of capacitance here, right? Capacitance is asked. So squaring it, nu square is 1 by 4 pi square into LC. Okay, then the capacitance value C is equal to 1 by 4 pi square, 1 by 4 pi square, L nu square, L nu square. Clear? 1 by 4 pi square L are fixed values, and as nu varies, capacitance varies. When we put the minimum nu here 800 kilo, we get the maximum capacitance. Or when we put the maximum frequency 1200 kilohertz here, we get the minimum capacitance. Okay, suppose I am putting the maximum frequency 1200 kilohertz here, then we get the minimum capacitance C minimum. C minimum is equal to 1 divided by 4, and pi square I am taking as 10. Pi square taking as 10. Okay, now inductance value is equal to 200 into 10 power minus 6. See, 200 into 10 power minus 6 is 2 into 10 power minus 4. 2 into 10 raised to minus 4. Okay, now see, I may place this value here. This capacitance is equal to, see, capacitance is equal to, like here. The minimum capacitance C minimum is equal to 1 divided by 4 into pi square is approximated as 10. Then L is equal to 2 into 10 raised to minus 4. Okay. Then the maximum frequency 1200 kilo. 1200 into kilo. Kilo is 10 raised to 3. Then what we obtain here? 10 into 10 raised to minus 4. That is 10 raised to minus 3. Into 10 raised to 2. That is 10 raised to minus 1. Into 10 raised to 3. That is 10 raised to 2. Isn't it? So 10 raised to in the denominator, and we get 10 raised to minus 2 in the numerator. Once again, 10 into 10 power minus 4 is 10 power minus 3. Into 10 raised to, that is 10 power minus 1. Into 10 raised to 3, that is 10 power 2. To the numerator, 10 power minus 2. Good. Divided by 2 into 4, 8. Then 12. Now, 8 into 12 is equal to 96. Clear? 96. So, I am taking here 100, then divide by 100. Then 10 power minus 2 divided by 100 is 10 power minus 4. Then I can write 100 divided by 96 into 10 raised to minus 4. Okay. 10 raised to minus 4. See. Now what we will get? What we will get? See. 100 divided by 96. Some of the values are missed here. See. Nu is equal to omega is equal to 1 by root LC. Okay. Nu is equal to 1 divided by 2 pi into root of LC. Omega square is 1 by 4 pi square into LC. Then C is equal to 1 by 4 pi square into L into nu square. Yes. Here this should be squared. Yes. Okay. 1200 into 10 raised to 3 should be squared. That's well. That's the problem. 1200 into 10 raised to 3 should be squared. Now we can check the value. See what happens. Listen. 10 into 10 power minus 4 is 10 power minus 3. Then this is 10 raised to 2 into 10 raised to 3. That is 10 raised to 5. 10 raised to 5, the square is 10 raised to 10. So here it is 10 raised to 10. And then 12 square is already there. That we will write later. Then this is 10 raised to 5. 10 raised to 5 into 10 raised to minus 4, that is 10. 10 into 10, that is equal to 10 raised to 2. 10 raised to 2. Isn't it? Yes. 10 raised to 3 into 10 raised to 2, that is 10 raised to 5. And the square of 10 raised to 5 is 10 raised to 10. Square of 10 raised to 5 is 10 raised to 10. 10 raised to 10 into 10 raised to minus 4 is 10 raised to 6. 10 raised 6 into 10 is 10 raised to 7. To the numerator, it is 10 raised to minus 7. That's finally 10 raised to minus 7 divided by, no, you're right, 2 into 4, 8 into 12 square. 12 square is 144. 144. Okay. Yes. Yes. Then 8 into 144. 8 into 144 is 800 plus 320 plus 32. 320 plus 32 is 352. 352 plus 800 is 1152. So 1 divided by 1152 into 10 power minus 7. Clear? Yes. Then we can take here 10,000. 10,000 divided by 1152. Then here it will be 10 raised to minus 11. 10 raised to minus 11. Okay. Otherwise we can take here as 1 lakh. Then it will be 10 raised to minus 12. And 10 raised to minus 12 is picofarad. 10 raised to minus 12 is picofarad. Isn't it? Okay. So I'm taking, first of all, I'm taking suppose 1000 divided by 1152. Then it will be 10 raised to minus 10. Okay. And 1000 divided by 1152 is approximately 0.9 in that range. 0.9 in that range. Okay. That is 0.88. 0.88. 0.88 into 10 power minus 10. That is 88 into 10 power minus 12. That is 88 picofarad. See, this is the answer. 88 picofarad. No other options like 88 there. So the answer of this question is option B. Understand? Now, if we put here 800 kilohertz and square it, we will get 108 picofarad. That we can easily check. I think you understood the question. Very simple one. Okay. Moving to the next one. The figure shows a series LCR circuit connected to a variable frequency and 220 volt. Okay. This is a variable frequency, 220 volt source. The source frequency which drives the circuit in resonance will be. If frequency is varying, then the impedance will be varying. Because we know the impedance is equal to root of XC minus XL all square plus R square. Yes. As the frequency varies, XC and XL varies, accordingly Z varies. At a particular frequency, XC and XL becomes equal. At that moment, Z becomes minimum. The condition is known as resonance. Okay. At what frequency the circuit will be in resonance? That is asked. The resonant frequency is equal to 1 divided by 2 pi into root of LC is the formula. 1 by 2 pi into root of LC is the formula. Clear? Okay. We can substitute. 1 divided by 2 pi into root of L value is 5 by pi. Isn't it? 5 divided by pi. Okay. And C value is 20 by pi micro. 20 divided by pi micro, 10 power minus 6. Clear? Pi into pi, pi square. Root of pi square is pi. 1 by pi and this pi cancelled. Cancelled. So pi is cancelled. 5 into 20 is 100. Root of 100 is 10. So this will be 1 divided by 2 into 10, that is 20. Now, root of 10 power minus 6 is 10 power minus 3. To the numerator, it will be 10 raised to 3. Clear? 1000 divided by 20. 1000 divided by 20 is 50. Okay. 50 hertz is the answer. 50 hertz is the answer of the question. Okay. All questions are very direct and simple. By solving these questions, we get a clear idea of the concepts discussed in the chapter. Okay. Keep up your good work. Study well. See you soon. Thank you.